Hello, everyone. In the first chapter, I would like to talk about digital systems in general. What do we have as a digital system? How do we use digital system? And what this course is sitting, where this course is sitting in the digital system, and what are we going to learn this term? I'm going to talk about them briefly, and we'll introduce the binary numbers. How do we use binary numbers? You have seen decimals and some other bases as well. We will introduce the base 2, which is binary numbers, and we'll talk about how things are working inside of a computer or any digital system. And then we will deal with the binary numbers in details, doing arithmetic operations, conversions between different bases, and so on. And then we'll introduce some physical side of the where we keep these binary numbers, how do we play around with these binary numbers in digital systems, and we will also talk about the codes and etc. Now, the first chapter is the one of the important ones because we are going to talk about and give you the basics of logic design and digital design. Okay, so let's start with the digital system. Now, when you consider the world nowadays, you can easily spot lots of digital devices around us. Mobile phones, digital TVs, laptops, even washing machines, dishwashers they are all digital. And we can say that we are living in a digital age. And as we all know that the world around us is analog, we are actually using this analog data around us, converted some point to the digital, and use that data as digital. So we'll talk about how these are coming up in the digital system, but I'm not going to go into the details of those in this course. So this is going to be the first chapter in the textbook. Let's start with the digital systems in general. So, as I already said, we are living in a digital age. Robotics, tablets, cars, home automations, everything, we can look around and find out that there are some digital bits in there. Okay, so we are living in a digital age and we have to cope with it. So when we consider this digitalization or the devices around us, what do we have in general is a simple architecture. And this architecture is based on a typical embedded system. So what do we have? We have got some analog devices because as we already said, the world around us is analog. We have to use those analog inputs and convert it to digital using analog to digital converters. Then this is our brain, which is a microcontroller or a microprocessor or digital signal processor that we do some operations on the data. Maybe we can keep it in the memory, or we can send it somewhere else as a digital output, and so on. You might have a digital inputs as well from some other devices, or if you want to have another analog output, then you have to convert it back to analog and send it out. So this is a typical system. And where this course is sitting and what we are going to talk about is mainly the microcontroller or processors. So what do we have inside of those microcontrollers and the processors? That what we are aiming for. Okay, so when we talk about digital systems, digital age, the computers and general purpose computers can be, or commercial applications like robotics, or maybe supercomputers for scientific research, or simple consumer electronics, telephones, digital cameras, and electronic calculators, etc. These are all part of our digital world nowadays. And when we talk about digital, we know that we are talking about discrete information. We know the specific value of the data. Okay, so it's not like an analog continuous signal. We have got discrete information processing, and that's what we are interested in. And that's how we are using the data in digital. So we can give an example of a typical digital processor or a general mobile processor, which is Ice Lake Intel processor, which we have got 4 cores, some imaging and graphics modules in there, memory controllers, and some other media encoders and so on. So this is a typical 10 nanometer CPU. Now, what do we need to know about is the first question comes, how does computer operates? Or how does this microcontroller or a microprocessor operates? This is the first question that we need to ask in this course. Because first, we have to understand the fundamentals. We have to understand the basic, how computer understands the data, how computer manipulates the data or process information. What is the physical phenomena behind it? This is what is important in the first lecture. And starts from, we need to ask the question, I don't know if you heard about binary numbers before, but binary numbers, so we have got 1 and 0, okay? And why do we have 1 and 0? Why computers or microcontrollers are using ones and zeros? This is the first thing that we need to ask. This is the first thing that we need to understand. And think about it. Try to think about a solution to it. Why 1 and 0, not 3, not 4, not 5, or some other numbers? This is also known as true or false, or maybe on and off. So these are all acceptable terminologies that we can use for 1 and 0. But why? Why is it 1 and 0? To be or not to be, or something else? Now, this is coming from the physics. This is coming from the physical phenomena. Now, if you think about a simple light switch, where we have got a switch and connected to a battery, and we have got a bulb. Okay, so when you turn the switch on, okay, or closing that switch, we are allowing the current to go through, and the bulb will be on. Okay, so everything depends on the switch over here. So what can we say about this? If this switch is on, that means bulb will be on, right? So that means we are using switches, either we turn it on or it is off. So again, it's coming to this point. Now, you might ask, okay, so we have got switches in our processors? Yes, we have got switches in our processors. So what are those switches in our processors? If you know, so dot switch that we can talk about in a 10 nanometer or maybe less, this is a typical physical device. It's a switch. In electronics and microelectronics, nowadays, we are using transistors. Now, transistor, it's a switch. Maybe you heard about it. In Intel processors, we have got nowadays, we have got 100 billions of transistors, 10,000 transistors, 1 million transistors. These are what we are having in a single processor. So what does this transistor is doing? This is called gate. This is called drain and source. Okay, so this is a typical NMOS transistor, as we call it. Now, what's happening when you apply a voltage to this gate, that means you are turning on the switch. Okay, so you are turning this switch on, so you're allowing the current go from one end to the other. This is what's happening with the transistor as well. It's a switch. And we have got actually two types of transistors. That's why we call them CMOS, which is known as complementary metal oxide semiconductors. Okay, so we have got two types. One of them is called PMOS, other one is NMOS. The difference is that bubble. Okay, so the gate, source, drain, gate, drain, source, and their legs are different based on their connections. Now, this complementary transistors, they are actually complementing each other. So, as we already said, when we apply a voltage, positive voltage over here, like 3 volts, 5 volts, and so on, we are allowing the current to go through. The PMOS transistor, this is NMOS, the PMOS transistor is other way around. When you apply a 0 volts, you're allowing the current to go from one end to the other. That's the difference between PMOS and NMOS. They are complementing. So when this is on, when you apply a 0 volts, this will be off. Because the gate over here is 0, you're not allowing the current to go through. Okay, so inside of a digital system, the tiny little, let's say, the cell or a switch is actually a transistor, which allows you to switch the data on and off, on and off. Keep repeating these steps and processing some information. Okay, so this is how we are using ones and zeros by turning on and off these transistors and process digital information. So what do we have in a typical digital system, or how do we design a typical digital system? Now we have got two approaches. One of them is it's not old-fashioned, still we are using it, which is a custom digital IC, because if you want to create something custom, you have to build your own libraries. You cannot use pre-built libraries. But in a typical FPGA programmable logic, which you are going to use in your labs, you can use pre-built libraries, you can use pre-built gates and so on. It's more, it has got more standards. But the steps that we are going through are similar. So architectural design is common for both because you have to define your processor, for example. 8-bit, 16-bit processor, you have to state that. Pipeline processor, RISC architecture, Harvard architecture, whatever you are going to use, you have to specify those. Then logic design. Now, logic design is what we are considering in this course. We have to know each logical block. Arithmetic logic unit. What do we have over there? We have got an arithmetic unit. What do we have inside of an arithmetic unit? So we can think about it this way. Processor. Okay, so inside of a processor, we have got ALU, arithmetic logic unit. And inside of an ALU, we have got arithmetic unit. And inside of an arithmetic unit, we have got adder. And inside of an adder, we have got gates. And inside of these gates, we have got transistors. Okay. Now, what we are interested is not the transistors, but we are interested in adder, gates, arithmetic, and ALU. This is what we are going to consider in this course. Transistors, it's another course, 4th year VLSI design. So let's forget about that now. Now, logic design is where we have got the gates. So transistors, we know there are gate transistors inside of the gates. We are just going to use those symbols to define a logic function. And then combining those gates give us a function of an adder. Combining that adder with some other gates and the logic blocks, we can have an arithmetic unit. Arithmetic unit combined with a logical unit, you will have arithmetic logic unit. This is what we are going to design in your labs as well. So circuit design is also part of the design flow. So when you define your gates, you can have a circuit design using transistors if you are building custom ICs, because you need to have a specific function over there. That's why you need a circuit design. So that's the missing part in the logic design FPGA, because you don't need to have a specific circuit over there. You are just using pre-built libraries. Then silicon validation means we have to validate the transistor designs and then verify everything, put on the chip, and send it to fabrication. Once that is done, we have to verify and validate that the silicon is working and everything is fine. So once that is done, we have to define the firmware for it. How is this going to function? Okay, so that's part of the firmware. So over here, when we design the logic, other gates and so on, we do a system validation. So system validation, we validate the design of, for example, ALU. We verify functionality and we validate everything on FPGA. Then it's fine, it's working perfectly fine. Then we design the firmware for it. So logic design, Boolean algebra, theorems, which we are going to see in the next chapter. So it's part of this design process. And engineers working on logic design and verification are experts in this area. And engineers working any portion of the design flow, they need to have the logic design knowledge in an excellent level so that they can achieve good quality designs. So let's see that abstractions that I have described already over here. The device is the transistors that we were talking about. So a simple device or a simple transistor is just a tiny device, just a few microns, which we need to use microscopes to see them. And then when we combine a couple of devices together, we can have a circuitry or a gate, let's say. And this is a typical inverter. I will explain the functionality of it. Then we define, based on the circuit, we define a symbol, a gate for it, okay? So that's another abstraction level, one level higher. Then we use those gates, combine them together, and then we have got arithmetic unit, as I already described here in the previous drawing. So arithmetic unit, combination of the gates, which we create a module. Then we put this module into another module. We create ALU, and then we create a system. So the processor. Okay, so these are the abstraction levels that we need to take care. And what we are interested, again, the gate design and the module design. Okay, we don't care about the circuit or device level or the system level. Circuit and device is a 4-year course. System level, which we just use a microcontroller or a microprocessor, is a 3rd-year course, which is 347, which you can take in next term. Okay, so as we already mentioned, the physical devices in the digital systems, then let's talk about how these digital devices are interacting with these signals. So transmitter on one side, we have got a transmission line and the receiver on the other side, and we send a signal. So typical real signal where we have got high voltage and the low voltage is just going on and off. You can see that there are some distortions, the noise, but you get the output from the receiver. Okay, there are some noise margins over there that we need to take care so that we can have a valid signals. In binary model, this is how we describe. Either it's going to be 1 or 0. It cannot be higher or lower for that. When it is 1, it turns on a transistor. When it is 0, it turns off a transistor. It cannot be in between. It cannot be degraded. Okay, so this is how we can model a typical binary signal. And the digital systems and analog systems, you know, most probably you know the difference. In a digital, we have got discrete values. We know exactly what this point is. But in analog, it's continuous and we just guess the closest guess that we can have. Okay, so the physical quantities or signals may vary continuously over a specified range. So digital signals, it gives us a greater accuracy. So let's introduce these digital signals and binary digital signal, which we just talked about 1 and 0. And information is actually represented with a physical quantity. Either it's 1 on or off, nothing else, or true or false, low or high, whatever you want to call it. But in the end, it's a physical quantity 1 and 0. So when we talk about the binary signal, logic 1 and logic 0, and when they're switching, anything in between that is undefined. Okay? So stable state is either logic 1 or logic 0. It cannot be in between. And in a typical positive logic that we call it, 1 is true or high, 0 is low or false. But if we consider negative logic, with the negative logic, true or high is 0, and false or low is 1. It's opposite. Generally, in this course, we are going to use positive logic, but you have to know what negative logic is. Okay? So this is important as well. All right, then. So now we know why do we use 1 and zeros? Because of transistors are like switches. So either they can be on or off. So we can just have 0 and 1, nothing else. Now, this gives us an opportunity that the digital signals are more having a greater accuracy, and they're actually going to be easy to understand because it's on a base 10. Either it's 1 or it's on base 2, either it's 1 or 0. It's not base 10 that you can have 0 to 9. It's not base 8 that you can have 0 to 7, or base 16, which is 0 to F or 16. So you just have two alternatives, and it's easy to deal with it and do some operations or do some calculations. Okay, so when we talk about binary numbers, let's first give an example of a typical base 10 number. Now, base 10, if you do remember from your secondary or high school, what do we have? 2 over here, 10 to the power 0 because of after the decimal point, then 10 to the power 1, 10 to the power 2. Then this is 100, this is 10, this is 1, and these are the weights, and we just multiply out them, and we sum them up, and we get 512. And over here, 10 to the power minus 1, minus 2, and it goes like that, and we use that one again, multiply with the weights, and we get the number. Okay, so this is a typical base 10 operation, decimal operation, which you already seen them in your secondary or high school. Now, base 8 is also similar. So rather than using decimals 0 to 9, we are using 8, so 0 to 7. So we have got 8 digits. The maximum that we can have is 7. Again, the same number can be applied. So if it is going to be in base 8, then it's going to be starting as a base 8, 8 to the power 0, 8 to the power 1, 8 to the power 2, and it can go like that, or a to the power minus 1, minus 2, and it goes like that as well. And the operation that we are doing is just changing the weight, the base over here, and based on the weights, we multiply them out, and we get the number. Okay, and for the 16, it's also same. 16 is base 16, so it starts from 0 and goes up to 15. But one thing about the hexadecimal numbers, anything greater than 9 are represented with letters. So A, B, C, D, E, F is 10, 11, 12, 13, 14, and 15. So this is base 16. And again, let's say 1, E, 5.78. Now 5 is 16 to the power 0, as we are using base 16. 16 to the power 1 and 16 to the power 2. Then you just do a simple mathematics, and these are minus 1 and minus 2. Then you just use the weights. So 1, E is what? E is 14. 5, 7, A is what? A is 10. So 10 times 1 over 256. Then you sum them up and you get the decimal equivalent value of it. Same applies for the octal. So if you just separate these out, you get a decimal equivalent of that octal number. So 512.74 in base 8, it's going to be equal to 330.9375 in base 10. You can see that there are lots of numbers over here. Then if this number is larger, then you have to deal with the powers of 8, like 8 to the power 8, 8 to the power 10, 11, 12, and so on. Now, when we consider binary numbers, this is much more easier than that. So for example, we have got 101.01 binary operation, which we have got base 2. Now, when we know that base 2 is just ones and zeros, and when you multiply something with 1, you are going to get the same value. You multiply something with 0, you are going to get 0. It's actually making our life much more easier than any other base. So let's take care of this. 2 to the power 0, 2 to the power 1, and 2 to the power 2. And over here, 2 to the power minus 1, and 2 to the power minus 2. And we have got a dot in between again. So 2 to the power 0 is 1, 2 to the power 1 is 2, and 2 to the power 2 is 4. And on the other side, 2 to the power minus 1 is 0.5. And then 2 to the power minus 2 is 0.25. So now we just need to look at the weights. 1, 0, 1. That means 1 times 4 plus 0 times 2 plus 1 times 1, because they have to be multiplied with the weights. Then dot 0 times 0.5 plus 1 times 0.25. Let's put times 0.25. So we know that this is going to be 0, this is going to be 0. 4 plus 1 point 1 times 0.25, so it's just 25. 4 plus 1 is 5, is 5.25. Again, base 10. Okay, it looks like a conversion from base 2 to base 10. So that means 101.01 is actually equivalent to 5.25. Okay. Now we can try different numbers, we can try different bases, and you can see how easy is the binary numbers that we are going to use, which we just have ones and zeros. So this is a typical example where we have got the decimal number 729. So 9 to the power 1, 10 to the power 0 for 9, 10 to the power 1 for 2, and 10 to the power 2 for 7. And you just use the weights and multiply them out. Now, binary number of that, if you want, we can try it. it's gonna be a huge one. So 1, 1, 0, 1, 1, 0, 0, 1. As it is base 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And these are all powers of 2. Okay? So rather than wasting a space over there, so they're all powers of 2. We know that when something is multiplied with 0, it's going to be 0, so I'm just canceling those out. Now, what is 2 to the power 9? 2 to the power 9 is 512. You'll get used to this. You have to learn it. After a while of you practicing, you will notice that you will start to remember. 2 to the power 8, 256. 2 to the power 7 divided by 2, 128. So this is going to be 128. And then 2 to the power 6 divided by 128 divided by 2, it's 64. To the power 5, which is cancelled out because of 0, is 32. To the power 4 is 16, 8, and to the power 0, it's going to be 1. So if you sum this up, you will end up again 729. Okay? And for hexadecimal, which we have got 2d9, 16 power 0, 16 to the power 1, and 16 to the power 2. Then you find those out and you add them together. Again, the result is 729. So you can see from each of these that when you convert them as a base 10, you are going to get the same number as this one. Okay? Even in octal, you will get 729. Okay then, so one thing that each of you that needs to learn this week is counting based on the powers. So what you need to know, 2 to the power 0, it's 1. 2 to the power 1, it's 2. 2 to the power 2, it's 4. 2 to the power 3, it's 8. 2 to the power 4, 16. 2 to the power 5, 32. 2 to the power 6, 64. 2 to the power 7, 128. 2 to the power 8, 256, and it goes like that. So 2 to the power 9 is 512. 2 to the power 10 is 124. So you have to learn this. Don't memorize it. You have to learn it. It's just doubling. They are just powers of 2. So 2 to the power 11, again doubles, 248. 2 to the power 12, 496. To the power 13, it's going to be double of that, and so on, so forth. So to the power 20, it's going to be 1 mega. 30 is 1 giga. And to the power 40, we are talking about 1 tera. Okay, so you have to learn the powers of 2. You have to learn them really well in order to quickly calculate some stuff. Okay.